is my first semester as senior second. And maybe the most important thing I want to say is this. I have a friend, an old colleague, working in a similar research field, and a number of years ago he decided to move to New York and accept a job in a hedge fund. Actually a hedge fund run by that. And as far as I gather from our mutual friend, he's now comfortably well off, which is great. I'm glad that my friends do that. I think I have a better job. I know I have a better job. I have a job that makes me really happy, and it's because of all of you here. This is one of the most, to me, seeing what you have all been working on for the last few months, and this is a culmination of several years of study. It means a lot to me. This is why I do this. I imagine my colleagues might say this. So I'm very excited to hear all of your senior talks. I'm also sad because after these, we're going to split into two groups starting next week, and so then I'm going to hear some of them, and you're going to hear some of them. And then at the very end, in April, we will get back together to the final season and month. Today, I'm just going to say a few things of a general nature. So each of you will be being introduced by someone, and so the 6 introducers, you know who you are. Each of you will be, twice this semester, you will be assigned to ask a question at the end of each talk. And so I'm hoping that all 12 of you who I assigned today will receive those emails. Can I see 12 hands? 11-ish? I guess it will work out. But I also want everyone to ask questions, because that's part of giving a talk, is responding to what people have to say and then creating some excitement and participating that way. I think that's it. So I'd love to introduce Bharat, but it's not my job to do so. Ben? Yeah, over to you.
So our first speaker today will be Bharat. Bharat and I were in the same ID1 together in freshman year, where we were doing Japanese and Japanese American literature. We also studied Japanese language together. And then Bharat went on to minor in Japanese, and then also studied abroad in Tokyo for 5 months. When I met Bharat, he wasn't actually a math major, he was a computer science major. But then he took points to show his linear algebra class and changed his mind and showed math instead. There's a lot of things you probably don't know about Bharat, but we don't have a ton of time to talk about them. But just a few things is that Bharat actually has black belts in both Taekwondo and Arnis. Yeah. And then I've actually never seen Bharat be frustrated. Like, he has this innate ability to really enjoy that feeling of being stuck on a problem for hours on end, which is a feeling I think we're really familiar with at this point. But Bharat really smiles whenever he's stuck. It's very enjoyable to see. So it's not really a surprise that he chose a thesis topic that allows him to explore high-level mathematics along with games at the same time. So without any talking, Bharat's going to tell us about the mysteries of Rubik's Polyhedra.
Thank you so much for that introduction, Ben. So before we really get started, I want to get a good gauge of the audience. So raise your hand if you've heard of Rubik's Cubes. All right, basically everybody. Now raise your hand if you've had a chance to play with the Rubik's Cube, manipulate a Rubik's Cube. Fewer. Now keep your hand up if you've solved a Rubik's Cube before. Now keep your hand up if right now you can solve a Rubik's Cube in under a minute. Yeah. So, clearly, Rubik's Cubes are satisfyingly simple. They're so popular, nearly everyone knows about them, but they're so beautifully complex, no one really understands them. Rubik's Cubes are also really important to me personally. This here is actually my very first Rubik's Cube. As you can see, it's a bit worse for wear. When I was younger, I used to play with it until someone came and talked with me once they were interested. I would teach them a thing or two about Rubik's Cubes and then make a new friend. So in the hopes that at the end of this, all of you will be my new friends. There we go. I need this. All right, so I want to pay attention to this side skin over here, so we can talk about the mechanics of the cube. So we have 6 faces, and each face has 9 little facets. And so we have a total of 54 facets. But each face has a center which is immovable. No matter how you turn it, the center won't move. And so we say we have 48 movable facets. Now, in the cube as well, we have 3 facets on this corner piece, and we have 8 such corners. We have 2 facets on this edge piece, and so we have 12 edge pieces. And of course, we have finally 6 center pieces. We call these cubies. And Rubik's Cube is all about how these cubies move. So how do these move? So we have 6 faces and 18 possible turns. Either a 90-degree clockwise turn, a 90-degree counterclockwise turn, or a 180-degree turn. So based on this, all of our 6 faces can be turned in these ways, and this is how we can describe how our cube moves physically. So now that we know how it works physically, let's look at how it works mathematically. And for that, we need some group theory. So group theory sounds pretty complicated, but it's pretty simple. It's any set along with some binary operation that's closed under these 4 axioms of closure, associativity, identity, and inverse. And let me give you a quick example. So a good group is the integers under addition. So our set is the set of all integers, negative and positive, and our operation is addition. So first thing, closure. If you take 2 integers and add them together, you get another integer. So we're closed on that. And the way you add integers, like 5 plus 3 plus 4, doesn't change how you do it. So we have associativity. Identity is we need some element that changes nothing with our integers. So that's 0 for us, because 0 plus 5 is always 5. And finally, we need an inverse. So we have some negative 5, such that negative 5 plus 5 equals our identity 0. And negative 5 is also an integer, so we're closed on inverses. Therefore, we have a group. Now, quickly, this is something that's not a group. Integers under multiplication fulfill the first 3 axioms, but our identity is 1. And so our inverse is 1/5 if you look at 5, because 5 times 1/5 is 1. But 1/5 isn't an integer, so we're not closed on the inverses, and so we don't have a group here. Now, naturally, the next step is to talk about the Rubik's Cube group. So the elements of the Rubik's Cube group are the actual turns of the cube and the sequences of turns. So like right, left, or any like sequence of turns is an element. And then an operation is just doing one turn after another, like right and then an upturn. So when you have something like this, we can easily see that the order in which we do the turns is clearly important. So we don't have something called commutativity, but the way you clump them up when you write them does not matter. So we do have associativity. And our inverses are just when we invert each thing. So we did an upturn, we do an up prime turn or up inverted turn. Then we can get back here, and we can similarly do a right inverted turn to get right back to the solid cube. Another thing that's important to understand about how this cube moves is the generators. So we have 6 generators, right, left, up, down, front, and back. And the generating set is simply a subset of our group, such that every single element can be expressed as some combination of those. So whenever we have a right R prime or R inverse, that's simply doing 3 right turns, because this cube sort of moves in a circle. And then same thing, R2, which is a 180-degree turn, is the same thing as doing 2 right turns. So every single possible combination can be expressed with some right, left, up, down, front, and back turns, which is great. So now that we know a thing or two about our group, next thing we can ask is how big is our group? So for that, let's look at the physical cube. So we have 8 corner pieces, and so we have 8 factorial ways to permute them amongst the cube. So let's get that up on there. Now we also have 3 facets on each face, meaning we can rotate the corners in 3 possible ways. And since we have 8 corners, this might lead you to believe we have 3 to the 8 ways to orient the corners of the cube. But in fact, we have 3 to the 7, because the final corner's orientation is determined by the previous set of corners. So we have 3 to 7 up there. And now let's do the same thing with the edges. So we have 12 edges and 12 factorial ways to permute them, and each edge has 2 facets. And so we have another 2 to the 11 ways to permute them. Again, not 2 to the 12 for the same reason. Now the centers, again, don't move and don't do anything, so they don't actually contribute anything to this number. Now it might seem like we're done now, but there's actually one thing we haven't considered, and that's parity. So when I turn the cube, you can see that this piece swapped with this piece swapped with this piece, and this piece swapped with this piece, and this piece swapped with this piece. Now, the way that things swap doesn't really matter, but what matters is the number of swaps. And for the Rubik's Cube, the number of swaps is always even. And this is what we call parity. So we want to remove all the odd parity elements from our group, and for that we divide it by 2. This leaves us with a pretty monstrous number, 43 quintillion. This is called the cardinality of our group, or the size of our group. And this is the number of elements we have. And to put this into perspective, if we had one element for one cube for every single one of these elements, and we stack them on top of another, this stack would be 300 light years tall, give or take. So now that we know just how monstrously big our group is, let me show you just how small our group is. And for that, I'm going to show you how to do some turns. So let's turn the right face, and then let's do it again, and then one last time, and we see we have come back to the solid cube. Now this seems pretty trivial, but let's take this notation and compress it a bit so it's a little bit easier to see. Let's call it R done 4 times, and let's see if it works with anything else. Let's do right, down, up inverted, right, down, up, sure, right inverted, down inverted, up inverted, right, down, up. And then it's still pretty scrambled, but if you do it one more time, we're back to the solid cube. And in fact, here's another one. If we do up, right inverted, up inverted, right. And we're back to the solid cube. Wow. Now this seems magical. Oh my god, how does this happen? How is this? It's amazing. So before we can talk about it, let's give it a name. This is called order. So the order of an element is the number. Slide. There we go. The order of an element is the number of times you can do it to itself to get the identity. Now, to be clear, I'm not saying you get back to the solid cube. You just get back to where you started. We started with a solid cube, so we're getting back to the solid cube. And so the order is just the number A, such that that works. So we can say the order of R is 4, and the order of right inverted, down inverted, up inverted, right down up is 3. So how does order work? What elements have order? How does any of this work? And to look at it a little bit closer, let's look at the first group we talked about, integers under addition. So let's take some integer like 5 and add it to itself, and add it to itself again, and keep adding 5 plus 5 plus 5. We'll never get back down to 0. So you can say 5 has infinite order. And the idea that things, when you add them to themselves, or you do them to themselves over and over, you'll get back to nothing, is a bit unintuitive. And this just shows how small the group is, because despite being 43 quintillion elements large, it's still minuscule compared to the infinite integers. And that's the big thing. Because if a group has finite order, then every single element, and a group has finite cardinality, then every single element has some finite order. And we know that the element with highest order in our group is of order 1,260. So this sequence of turns, if you do it 1,260 times, you'll get back to the solid cube. I won't demonstrate it for the time. And another quick theorem is we have Cauchy's theorem, which says that if there's a prime P that divides the cardinality of our group, then we know that there exists some element of that order. And previously solved for the cardinality of our group, so we found that we have elements of order 2, 3, 5, 7, and 11 necessarily, but we can also have any multiple of those. The order of an element also must divide the cardinality of the group. So because of this, there's no way to have an element of order 13, because 13 does not divide the cardinality of our group. So now we know a thing or two about Rubik's cubes. So let's forget about Rubik's cubes. So these are a couple variations. So this is the trivial 1 by 1 by 1 cube, my favorite. This is sort of a soccer ball. This one is the world record 33 by 33 by 33. This one's called the ghost cube. It doesn't have any colors on it, but instead the shapes move around the cube, and it goes from being a cube to not being a cube, and then you had to get it back into the cube shape, which is really hard. And to take my thesis, I'm focusing on these 4 plus the cube. the 4-sided tetrahedron, the 20-sided icosahedron, the 12-sided dodecahedron, and the 8-sided octahedron. And for the sake of this talk, I want to focus on these two. The 4-sided tetrahedron, commonly known as the Pyraminx, and the 20-sided dodecahedron, commonly known as the Megaminx. And here's a quick comparison between these. There we go. So all of these still follow the same rules of group theory that a Rubik's Cube does, but they are slightly different and they behave slightly differently when we do different things to them. So I want to start with the Megaminx and show you a corner rotating sequence. Now this is an element of order 3. So if you focus on this corner, if you perform this algorithm slowly, you can see that this corner has effectively rotated 120 degrees counterclockwise. And if you do this one more time, you can see you've made another 120 degree rotation. And if you do it one last time, our beloved corner has made its full rotation around, and the rest of the puzzle has been solved. Now, we just talked about order, so this isn't too surprising, but let's mix it up a bit. So let's expand this notation out, and let's slide some upturns in there. So let's do the same thing. And so our corner has rotated. Now let's slide this up, and let's do it one more time. And slide this up again, and one last time. And now that we've put 2 upturns, let's invert those as well. And we find that the puzzle is completely solved, and yet these 3 corners have each been rotated 120 degrees. Now, this is something we call a conjugate. So 2 elements are conjugate of each other if there's some element G, such that G composed with that, composed with its inverse, are the same. So for us, our G was the upturn, and so we took it up, and we did our sequence, and then we inverted our upturn. We just did that 3 times. And we find that this rotates all the corners without moving any of the other pieces. And this is actually very useful for solving the cube, because we can conjugate the cube into a more beneficial state, and then perform some quick set of sequences to get it into a solved state, and then undo what we just did, and we'll find that nothing really happened because these 2 things are conjugate of each other. Now, this is actually the first time I talk about trying to solve the cube, so let's try and talk about solving the cube with the Pyraminx. So one thing with the Pyraminx is that the corners are completely free rotating. They don't actually change at all. They on the cube. You can just twist each of the corners independently. And for this reason, we consider them to be trivial, because you can effectively solve the entire cube, the entire Pyraminx, and then just leave the corner cubies until the very end and just pop them into place. So if we're going to solve the cube and ignore the corners, let's just ignore the corners completely. And so let's look at the cardinality of our group. Is just 75 million, which is pretty small compared to the 43 quintillion we have in the whole Rubik's Cube, but it's still pretty massive. But if we completely ignore the corners, this drops dramatically to about 938,000. And even more, we have other group theoretic symmetries we can use. We can use some of the colors and some of the symmetries of the shape to then reduce this even further to a measly 11,520. So this is beautiful, because this allows us to both ask and answer the question, how many turns does it take to solve a pyramid? This leads us directly to God's number. I know, right? God's number is simply the minimum required turns to solve a puzzle, meaning no matter how you scramble up the cube or the Pyraminx, you will be able to solve it within this many turns. For the Pyraminx, the answer is 11. So no matter how much you scramble it, there is some 11 turns that will solve it, guaranteed. With the Rubik's Cube, that number is 20. So no matter how intensely you scramble it, there is a way to solve it within 20 turns. For the Megaminx, we have absolutely no idea. Again, like these are very complicated puzzles with a lot of potential. Even the Rubik's Cube took decades to find out what God's number was going to be. And for us to find out the God's number of other puzzles, and learn more about these puzzles, there's still a lot more math to be done and a lot more puzzles to be solved. And with that, thank you so much. It's been an honor to be the first one and kicking off this set of teacher talks. And yeah, the floor is now yours if you have any questions to ask me.
And Bharat's designated question askers are Thomas and Karina, but everyone else is also welcome.
Hi, could you go a little bit more into like the concept of like the God's number? Like how did they get it? Like are there ways to like optimize it even further, or is that like proven to be the smallest number?
Great question. So one, yes, it is proven to be the smallest number. So the way it was done is through computation. So as I showed before, when we reduced the number of possibilities for the Pyraminx, once we reduce it down to a pretty small number, we have the computational power to literally solve every single one of those things. For the Rubik's Cube, it wasn't quite like that. So what we did for the Rubik's Cube, because 43 quintillion is a lot harder to reduce than 75 million. And even true for this, which the order for this one is about somewhere on the tune of like 10 to the 100 and something. So it's pretty big. And there are other puzzles that are even higher. And so for those, we try to reduce cases into subgroups that can be easily solved. And that we use conjugates as well. It's a bit more complicated, but the main thing to understand is once we reduce it to a point that's computationally possible, then we can do it computationally. For the Pyraminx, we know exactly how to solve every single one, but for the Rubik's Cube, we don't actually know exactly how to solve every one. We just know that it can be done within 20.
So, is the reason why each one can't be solved because everything's just done very brute force, like there are heuristics to just go ahead and solve each one, or is it just, and why is it not possible computationally to do this if you already have a theory around?
I mean, so it's not like we can't solve it. There's definitely ways to solve it pretty well. Like every single one of these can be solved by computers and people. But the hard part is trying to find how to solve it in the minimum number of turns. And for that, we need to try multiple tries, and we need to have different strategies for that as well. So that's where it can get complicated, especially for something like this where there's a lot of phases. And so there's some ways to simplify things where you can sort of combine moves. But yeah, so it's not quite as complicated to solve them, but just solve them in the minimum possible terms.
So I believe it was Polyhedra when you talked about this. So for 3 by 3, you divide by 2 to calculate the possible number of turns. So does that, when you divide by 3, and that's like for an odd number, does that mean that if you have something like a 4 by 4 or 6 by 6, that it would possibly be simpler to solve than maybe 5 by 5 because you don't have to divide by 2?
So for the reason we divided by 2 is because of the parity, and that's going to stay the same for all. All of them are going to have that same parity. All of the puzzles are going to have that same property, where the number of swaps is determined. It's either going to be even or odd depending on the puzzle. And so no matter what, we'll have to divide by 2. And in fact, some of them have to divide by more than 2 just because of how the parity works with the corners as well. But it is true, so some of the puzzles are definitely easier to solve than others. I would say, in terms of these, I would say that the Pyraminx is definitely the easiest, and then the cube, and then the dodecahedron, and then this is probably the hardest one. Because of those reasons, because even though it's smaller, the way that it moves is different. The dodecahedron moves very similar to the cube itself. So that's why some of them are easier to solve than others, and some of them can be easier to find solutions for than others.
This might be a silly question, but are there any 4-dimensional Rubik's cubes or Rubik's objects?
Yes, actually, there's plenty. There's actually higher dimensional Rubik's objects, not physically because that's kind of impossible. But if you go online and look for 4-dimensional Rubik's cubes, you can find 4-dimensional Rubik's cubes and try to solve them. And it's a bit hard to work with because it's 4-dimensional. But yes, they do exist and they get solved. well. And also to add to that, it showed the world record as a 33 by 33 by 33. But of course, since we're in the world of mathematics, we're not constrained by reality. And so if you go online, you can find like 100 by 100 by 100 cubes and 1,000 by 1,000 cubes that you can try and solve on your
Cardinality of Megaminx.
So the Rubik cube was 43 quintillion. That's about 4 times 10 to the 29. And the Megaminx is about 4 times 10 to the, I want to say 101. It's a lot bigger. And even more, like the other, the icosahedron, which I'm also studying, is even more than that because it's even bigger.
One last question.
Are there like other like Rubik's objects that aren't, say, colored polygons? Like is there like an applied Rubik's like a reality?
I mean, there are Rubik's cubes that don't use color. Like I showed one that used shapes instead. And there are also cubes that use color and shapes, that they completely like shift from being a cube with other shapes and then get them back into being a cube or any of the other shapes. So I'm not sure what else you mean by like other types of cubes.
I mean, like, could you apply this like Rubik's theory to something that's not obviously a Rubik's cube?
Yes. So the Rubik's cube fundamentally is just a part of group theory. So in fact, the Rubik's cube is symmetric. It's isomorphic to a subgroup of the symmetric group, which makes sense to algebras, not to anyone else. But because of that, every single one of these can be described using mathematics, and there are other objects that can also be described using the same mathematics. And so in that sense, we can relate the two through group theory.